in real DC machines, the way we calculate the amount of torque that are generated or induced in the DC machine will depend on the number of conductors that we have inside the machine. Because we've seen just now that each single conductor has its own forces, right? Induced on each of the conductor. So if we have multiple loops and multiple coil in a machine, then we have to calculate for each of the conductor. Now, we know that induced torque is 2RILB, right? Okay, so that's for the total torque that we have for two conductors inside a machine. So basically for one single conductor, it is RILB, okay? But since we have multiple loops and multiple coil inside the machine, the current that goes into each of the conductor will depend on how many current paths that we have inside the conductor. So the armature current that actually goes inside each of the coil will have to be divided with number of current paths before we will know how much current inside a conductor. So I here, if ICOND or I conductor here refers to the current that actually goes inside one conductor. Okay, so we know that the torque for each conductor is actually R times I of the current that goes through one conductor times L times B. Now we know that for the induced torque for the whole machine, we have to multiply for the number of conductor and its current path. Okay, so therefore, if we have the induced torque in total, we have to multiply this term, this term with total number of conductor. And we know that the total number of conductor is Z. Okay, that's why we have R, I conductor, L, B, okay, all of these times with Z. Or if we want to, since finding the number of conductor is actually coming from armature current divided by the total number of current path, we can also replace this term with armature current divided by number of current path times LB times Z. Okay, so that's how we get this term, okay, the induced torque, right? So from this term, okay, we can actually expand the term by replacing, okay, the number of path, okay, not number of path, but basically to come up with this equation, you are expanding the term to include the surface area of the pole. So if we consider that to come up with total flux, we know that it must be the magnetic field density times the surface area under the pole, right? So AP is basically pi RL, right? And will depend on the number of poles that we have. So if it is just two poles, then you will have 2 pi RL divided by P. Okay, so if you have 2 poles, then you have pi RL. If you have 4 poles, then you have to divide it by 4 and so on, right? So if we consider this term, okay, to be the terms for A, all right, so I will expand this term as a 2 pi RL times B, all right, and per P, okay. So since we are introducing the term 2 pi there, okay, to make sure that we are consistently following the variables that we are introduced here, we have to put 2 pi as well at the top and P. Alright, so that's how we get this term ZP over 2 pi A. Okay, alright, so therefore when we combine this together, you get flux. Okay, the total flux 2 pi RL as in A. 2 pi RL over P is actually A, and then B, when you multiply that together, it becomes the total flux. Okay, so the term at the front is what do you call, the machine constant. Okay, so this machine constant will, like I said in the previous slide, that will depend on the number of conductors that we have, which is Z, number of pole, as well as the number of current path, which is the current path will depend on whether you use retrogressive wiring or progressive wiring. Okay, so at the end, the real DC machines is therefore will depend on the machine constant, the total number of flux, as well as the armature current. Okay, so from the DC machines, we have these two that are induced when we have electricity, the magnetic field, as well as conductors. So you have induced voltage, which is equals to K phi omega, and you have induced torque, which is equals to K phi Ia. So the torque mainly depends on current. So if you have a higher current supply to the rotor, you will have higher torque. Okay, given that the magnetic field density is constant, and if you have higher speed, you will have higher induced voltage. Okay, so that is kind of a given, okay, or logic that we have if we wanted to operate our electrical machines. Okay, now we will move to power flow and losses in DC machines. Okay, so in DC machines there are two types, like I said, generator and motor. So the power flow will actually refer to what is the input and output for each of the machine. Obviously, for generators, we know that the input is the movement that we applied on the shaft to eventually get the voltage at the terminal. So the input power is actually equals to applied torque, okay, applied torque times omega m, or the speed of the motor or the rotor in radian per second. Okay, so if we know the applied torque and the speed of the rotor, then that is the input power that we give to generator. But then the losses will happen because of stray, mechanical losses, core losses. Before, at this point, if we eliminate, or not eliminate, minus all these losses, we will have converted power. So converted power is actually equals to the induced torque. Remember, we talked about induced torque just now, times omega m, which is equals to the induced voltage times armature current. Okay, so at this point, if we the converted power, if we minus the losses, the I square R losses because of the winding, then after that we'll get the output power, which is electrical power lah, the terminal voltage times the line current. Okay, so we can see here that the output power is much less than the input power, and it depends on the number of losses. Okay, alright, so on the motor, on the other hand, we know that the input is actually coming from the electrical supply. So you have terminal voltage and line current. So you will then there will be losses if you put the input power, the input electrical power, then it starts moving. Then the first losses that will occur is I square R losses, which is losses on the winding. Okay, so after that, if you minus this I square R losses, you'll have converted power. Okay, so this is what we call converted power. So converted power is actually equals to the induced voltage times armature current, which is also equals to induced torque times omega m, or speed of the rotor, in radian per second. Then this converted power will minus the core losses, mechanical losses, and stray losses before we have the output power here. Not P in here, is P out, which is equals to applied torque, the output torque times omega m. Okay. Alright. So losses in DC machines are, like I said, can be clearly seen here in the power flow diagram. So whenever you are required to draw a power flow, you have to draw it like this, because it shows how much power is that you lose from the input when you are operating your electrical machines. Okay, so the losses in DC machines are the copper losses that you see, which is I square R, which happens at the armature, which is your rotor, and the field, which is at your stator. Okay, and you also have a brush losses, because we talked about this before. When you have a change of current, and there will be a voltage drop, so you will have voltage drop times the armature current, which is typically assumed to be 2 volts. And then you have core losses. It varies with the magnetic field squared and the number of turns times, the speed power 1.5. Okay, so this is because of the hysteresis. We talked about hysteresis before this, as well as the eddy current losses. You will also have mechanical losses, which is referred to as friction losses. Okay, it can be because of the bearings, or obviously because you have bearings that are helping the motor to rotate in place, and windage losses, which is the friction of the moving parts with the air inside the casing. Obviously, we always have a gap, the air gap inside the machines. So the movement of the rotor against the air also have friction. So we call that a windage losses. So these mechanical losses, we typically doesn't actually calculate like empirically. So usually it's given as some kind of watt. Okay, and you also have a stray losses, which is by convention is 1% from the full load usage of the power. Okay, so the efficiency is obviously the output power divided by the input power times 100%. All right. Okay, so I think at this point we have looked at how induced voltage and induced torque has been developed inside the electrical machines, and this both of the term, or both of the variables are very important in determining the performance of your electrical machines. Okay, and we also look at the power flow, how the power that we actually supply get lost inside the process, and then how much power that we actually get from the machine. Okay, so before we move to equivalent circuit of DC motor, I would like you guys to go to the ULearn and give some feedbacks on the lessons that we have today, as well as answer a few of the quiz questions. Okay.